Hello all, and welcome to the final Physics 2212 lab video. I'm Colson Cunningham, and this is magnetic molasses. In this lab, we aim to explore the phenomenon of electromagnetic induction through Faraday's law by observing a magnet falling through a conductive tube of aluminum foil. Our objectives were to model this scenario in lab, to compare it to a model on VPython, same thing. Our results was that the average fall time for the magnet was 1.148 seconds, which, when using the computational model with a magnetic dipole of 1.5 from lab 3, predicted time to fall was 0.452, which is significantly less. To match the lab results, the model projected that the magnetic dipole would need to be 2.723. In this lab, delve into several fundamental principles of physics, including Faraday's law, which explains how a time-varying magnetic field induces an electromotive force, EMF, in a closed loop, which can drive an electric current. Next is the magnetic force on a wire loop. When an electric current flows through a wire loop, it creates a magnetic field. According to Lorentz force law, a magnetic force is exerted upon the wire loop when it interacts with an external magnetic force. And next is Newton's third law of motion, which states that every action has an equal reaction. So as the magnet is exerting a force onto the current inside of the aluminum, the current in the aluminum is also exerting force on the magnet. And finally is Ohm's law, which relates voltage, EMF, to the current and resistance. Here's the experiment. You can see the magnet is our system, surroundings being everything else, including the tube. The force is acting on the magnet, or the force of gravity, and the magnetic force from the loop onto the magnet. And you can see the current and electric field and the magnetic field on the loop. Here's the procedure. We're going to mark and measure the magnet as well as the tube, drop it several times, measure the time it takes, model this in VPython, and then compare the two. Here's the observational data. You can see trials 1.148 seconds to fall. And you can see we use this observational data here in the computational model. And putting this into our code. And now we're going to set up some functions. First is the magnetic field due to the dipole. And you might recognize this upper equation here. We use this in lab 3 as well to calculate the force, the magnetic field from the magnet. And then we're also going to calculate the change in flux, magnetic flux due to time, or with respect to time, I should say. And you might also recognize this. I briefly showed it at the start of this presentation, but we're going to input that here to calculate the change in flux. And then also we're going to iterate as we go, as the magnet goes throughout the loop, and you'll see the time it takes and the magnetic dipole output at the end, which is here. First, we're going to use the magnetic dipole moment from lab 3 of 1.5, and you can see this is the course it takes, and it takes 0.452 seconds to fall. So now we're going to calculate what the magnetic dipole moment of this magnet is according to our experimental value, and that was 2.723, and you can see that one here. All right, so a couple of discussion points. First, if the resistivity reduces, then the resistance is near to 0, which means that the current has to be really, really high according to Ohm's law, V equals IR. And as the current is related to the magnetic force by the equation on the left, a large current would mean a large magnetic force, which by Newton's third law would mean that there's a high force acting on the magnet, which means that it would take a lot longer to fall. Secondly, if there are holes or cuts, they would disrupt the continuation of the rings in the aluminum tube. These rings allow for the induced current to flow around the tube as the magnet falls. Disrupting these rings would reduce the induced current, which, again, as with the equation on the left, this induced current related to the magnetic force directly. So the magnetic force on the loop decreases, and through Newton's third law means that the force on the magnet also decreases. In the end, we found that the magnetic dipole moment from lab 3 may not be completely accurate, as we had a 61% error from the observed time. By increasing the magnetic dipole moment to 2.723, the simulation predicted identical time, which is 1.148 seconds, which is why we think that lab 3's data was inaccurate. And the results suggest that the magnetic dipole moment was very inaccurate, which may be caused due to friction between the magnet and the tube, air resistance, timing error, measurement error, and that can also be said for the side. We found that when we flipped the magnet around and dropped the south side in first, the magnet took more time to fall at the bottom, which was very curious. And if we use a ferrous tube, the magnet would stick to the side, which is occurring in the induction of the current in the aluminum rather than falling to the other side. Thank you.